So, in the last class we have seen how we can use KKT. We have looked at different cases, one with large amplitude perturbation, another with drift, potential drift. Now, what I want to describe is the following. So far we have said whenever there is an adsorption involved, we said that Langmuir isotherm model is applicable. The main reason we have done that is so that we can get analytical expression. When we expand the expressions in Taylor series and truncate after the first term, we could do all this easily when Langmuir adsorption isotherm model is used. But there are other models which might be more appropriate. They are little more complex, but if you want analytical solution, it is not easy, and in some cases it is not possible to get the analytical solutions. However, the last few classes we have seen that when we go to NLEAS, most of the time we end up using numerical methods. I want to show some examples where instead of using Langmuir isotherm model, how we can handle Fromkin or Temkin isotherm. Now, all these isotherms describe the equilibrium constants. In case of Langmuir adsorption isotherm model, this assumes that the equilibrium constant is independent of the coverage, fractional surface coverage. It assumes that if you have n number of sites, the probability of an adsorption occurring in a place, in our case a metal becoming metal adsorbed species, that is not dependent on the location of the site, whether it is here or here, whether it is near the center or at the edge. If it is vacant, the probability of adsorption is equal for all those sites, all the vacant sites. Okay. It does not matter whether a neighbor is an adsorbed species or a vacant site. It does not matter whether this location is at the center or at the edge. Okay. So, there is no interaction between the species. So, in the Langmuir, all sites are assumed to be equal and there is no interaction between the species. Okay. Another adsorption isotherm, it is called Fromkin isotherm. This says that there is an interaction between species. Sometimes presence of one species will reduce the probability that adsorption will occur at the neighboring site compared to a site where all the surrounding sites are also vacant. This is repulsive interaction. If you already have a species here, then if you look at the chance of adsorption happening right next to this versus an adsorption happening in these sites, this site has lower probability. Basically, the presence of an adsorbed species reduces the probability because there is a repulsion. In theory, you can also say that presence of a species enhances or increases the probability of adsorption happening right next to that. That is because of attractive interactions. This is one scenario. Another way to look at that is to say that you have n number of sites, not all sites are equal. So, if I have certain number of sites here, in the very beginning adsorption will occur only at certain sites, preference is given to those, and then it would occur at certain sites, and then third probably here and fourth here. These are described by the energy levels. In certain cases it is easier to adsorb, in certain sites it is harder to adsorb, and whichever is harder it occurs later. Temkin adsorption isotherm basically assumes that all the sites are not equal and there is a variation in the site quality, and Fromkin adsorption isotherm assumes all sites are equal in the beginning, and when adsorbed species is present in one place, then the chance of adsorption or the probability of adsorption right next to that is changed. If I look at the variation of the adsorbed species concentration versus concentration in solution, for example, the equation which describes the Temkin isotherm is similar to the equation which describes the Fromkin isotherm when repulsive forces are active. Now, I can give you an analogy. Imagine you go to a restaurant, you have n number of seats, and some seats might be occupied, some seats might be vacant. If we say that a new person who comes in will occupy any vacant seat, okay, without worrying about whether the neighboring seat is occupied or not. So, if it is vacant, the probability that the new person who enters will occupy that seat does not matter where that is located in the restaurant and whether the neighboring seat is occupied or not. As long as a seat is vacant, somebody might occupy it, the probability is same for all the vacant seats. That is Langmuir adsorption isotherm. In case of Fromkin isotherm, imagine that you go to a restaurant, you go to a table, in the table 2 are occupied, you are not likely to go to that same table and take the third seat or the fourth seat, right. You are likely to go to a place where it is completely vacant, a table where nobody is occupying that. So, this is equivalent to saying that all sites in the beginning are equal, but if some sites are occupied, then there is a repulsive interaction. That is, you are not likely to go to a place which is already occupied with few vacant seats right next to that. You are likely to go to a place where there is nobody around. Okay. On the other hand, if you know the people who are there, if you are friends with them, you are likely to go and join them in the table. That is similar to saying attractive interaction. So, if you do not know them, if they are strangers, you are likely to go to a place where it is completely empty. If you know them and you want to go near them or sit next to them, that is similar to attractive interaction. Now, it does not mean the seat is better or the location is better, it just means the location is better because that person is present there, or location is worse because somebody is present there. Now, Temkin isotherm, the way you can describe that is this: you have a restaurant, you have n number of seats, but some seats have better view. So, anybody who comes in will first occupy those seats. Okay. The ones which have poorer view probably will get occupied second. We do not consider the interaction between the species, that is to say, if you have a table where it is partially occupied, the view is very good. This scenario, it says that the third person who enters will go and occupy that table, though it is already occupied by somebody else, it is partly occupied by somebody else, but still because the view is good, new person will go in and occupy that table. This is just an analogy. In case of Fromkin isotherm, it does not tell anything about the rate constant, all that it tells is the equilibrium constant. So, if we have a simple reaction, okay, in one step, let us say K1 is the rate constant for the forward reaction, K minus 1 is the constant for the reverse reaction. Then it does not tell how K1 will vary or K minus 1 will vary, it just says the equilibrium constant, which is K1 by K minus 1, that is dependent on theta, that is all it says. And the dependence on the theta equilibrium, fractional surface coverage at equilibrium, is given by this expression. So, K equilibrium 0 exponential of beta theta equivalent. Although it does not tell anything about K1 or K minus 1, we can get this expression for equilibrium constant if we say that K1 or K minus 1 for the reverse reaction is given by an expression like this. K1 is given as K1 0, earlier we would have said K1 0 exponential B1 E, right, because we said it is Langmuir isotherm model, but now because it is Fromkin isotherm model, it also depend on beta 1 G theta. Now, G is the ratio of variation in del G, that is Gibbs free energy with respect to theta, that is in the numerator. The ratio of that to the factor RT, R is of course the universal gas constant, T is the temperature. Now, beta 1, beta 2 are called coverage parameters. In this case, beta 1 is for the first reaction, beta 2 is for the second reaction, and we say both these reaction rate constants are going to depend on theta. Now, we are going to assume that repulsive interaction is likely if part of the surface is occupied by M plus adsorbed. Site here is more likely to become M plus adsorbed compared to this site, because these two are charged species, it is quite likely that they will have repulsive interaction. Because of that, we are going to say if theta increases, if this becomes more, this reaction will slow down, but if theta is more, it is more likely that this reaction will happen faster. That is to say, k 1 will decrease with theta, and if k 1 has to decrease with theta, g of course is a positive number here, beta 1 has to be negative, beta 2 will be positive, then we can say when theta increases, k 2 will increase, k 1 will decrease. So, that is more realistic scenario. Now, we can write the mass balance equation, charge balance equation as we have done before. We would normally write for this, the mass balance equation will be k 1 1 minus theta minus k 2 theta, that would tell us gamma d theta by dt. Instead of k 1, we expand this and write it as k 1 0 exponential beta 1 g theta exponential b 1 e. The second reaction is a chemical reaction, therefore, it is independent of potential, but it is dependent on theta anyway. And the current is of course given by first step Faraday constant k 1 1 minus theta, second step does not contribute to the current, therefore, it is not shown here. Now, under steady state condition, if we apply DC, the fractional surface coverage will also give you a steady state value, we call it as theta SS. We can get that by setting these terms to 0. However, in the earlier case when we have Langmuir adsorption isotherm, it is easy to rearrange and get a solution for this. In case of Fromkin isotherm model, you can't get an analytical solution. So, you can set this to 0, that is straightforward, but we will have to use numerical method to solve this and get a value for theta SS. Okay. I want to show you an example. Let us say the k 1 value, b 1 value, k 2 0, b 2 is of course 0 here, gamma value, and at a DC potential of 0.3 volts versus OCP. AA capacitance is not relevant for this, but when we calculate the impedance, total impedance, we need that value also, and in that case we need to look at different AC perturbations, 10 millivolts or 100 millivolts. G value is taken as 20, typical values would vary between 0 to 20, it is a dimensionless number. So, we will keep it as 20 here. Beta 1 I have set it as minus 1, beta 2 I set it as plus 1. Those cases is of course, this is in voltage, sinusoidal perturbation. Okay. K 1 0, B 1, B 2 is set to 0, actually B 2 is not necessary, but it is already in the code. So, we set it to 0 because second reaction is chemical reaction, and this is actually G, for some reason it is written as R 1 in the code, and when we calculate the impedance, we will look into the value of frequency going from 100 kilohertz to 1 millihertz, 10 frequencies per decade, logarithmically spaced. In order to calculate the steady state value, what you have done is first rearrange this. You have this expression, bring this to the right side, you would get k 2 0 e power b 2 g theta multiplied by theta. Then bring this to the denominator, you will get theta divided by 1 minus theta SS, right. Then divide by exponential beta 1 g theta SS, you would get exponential of b 2 minus b 1. What is left is k 1 0 exponential b 1 EDC, that is one part. On the right side you would have got k 2 0, bring it to the denominator. So, you would have one expression A, another expression B, A minus B is set to 0. Okay. For a given value of EDC, we had to find a theta such that this is satisfied. So, what we can do is to write this as a f of theta. Okay. Find the absolute value of f of theta, and that is going to be minimum when f of theta is 0. It is a real number, it can be a positive or negative number, okay. And this number, when we take the absolute value, that is going to be the minimum when this f of theta is 0. Okay. So, what we have done is use a function called f min bound and say find theta. We set the parameters. If I want to change the value of k1 0, b1, k2 0, gamma or g, well, gamma is not relevant here. If I have to change g, beta 1, beta 2, etc., I can pass it using the vector p1. So, we can get the variable and parameter values in the first few steps. I am not showing all of them here because of space. And then we define something called error. Error is term A minus term B. This is theta divided by 1 minus theta exponential of g beta 2 minus beta 1 into theta. So, this tells the first term, and this is of course k1 dc partial, because k1 is k1 0 e power beta 1 g theta e power b1 e. So, when e is set to edc, this entire term will be k1 dc, but if we take only k1 0 and b1 e, we will call it as k1 dc partial, divided by k2. Of course, k2 is k2 0, but does not matter, we can still use beta 2 as 0, and that is going to be same as k2 dc partial. And we find the absolute value of this and minimize this. When we want to get the impedance, what we have to do is apply a DC, on top of the DC superimpose an AC, and then find the response. We find the theta response, we find the current response, we take the current steady periodic results, do the FFT, and then we know what to do. Okay. So, to integrate this, earlier we would have said k1 1 minus theta minus k2 theta divided by gamma, that is going to be d theta by dt, and in that case it would have been k1 0 exponential b1 e, but in this case it is little more complex, does not matter. If you are going to use numerical method, we can just substitute whatever expression we have to. This case, for example, I would have written it as d theta Frumkin for mechanism 1, and we get all the parameter values, variable values, and then first set the d theta by dt to 0. We calculate EAC, we calculate the potential E as a sum of EDC and EAC, and we will continue in the next page. This is the equation that we want to integrate, right. So, we will set k1 and k2 as k1 0 exponential b1 e exponential beta 1 g theta, k2 0, in this case b2 is 0, so it does not matter, and likewise for beta 2 to get the k2. Now, I have written this as term 1, term 2. So, k1 1 minus theta is term 1, k2 into theta is term 2, term 1 minus term 2 divided by gamma should give us d theta by dt. So, we want to write like this so that it is easier to debug. If there is any mistake in the code, it is easier to debug this way. And when you apply sinusoidal potential, this is integrated for about 2 seconds, 1.5 seconds. You can see that it oscillates, it drifts, and then achieves steady periodic result after some time, perhaps after half a second, definitely after 1 second. Okay. So, we have seen this in Langmuir-Isouta model, it is going to come in Frumkin, in Temkin, any of these absorption Isouta models. We had to look at this, we had to ensure that steady periodic results come, and then we had to take the data. Okay. So, for example, the default tolerance value is 1e minus 6, if you remember right, okay, in the MATLAB. If you want little more accurate value, you have to change that. This integration works well when you use ODE 15S, because the equations happen to be stiff equations. Okay. When we are looking at analytical solution, we never had to worry about what type of equation it is. Now, when you are going to use numerical method, you have to use the correct solver, ODE solver. If you have stiff equations and you use the normal solver, either it will not give you the result or it will take very long time and give you some results. Okay. So, initially we wait for certain time, we calculate the number of cycles based on the frequency, wait for certain time, and then integrate for some more time, n number of cycles. I have not shown you all the details. So, this first part is for waiting, second part this t is a little different, it is based on the frequency, based on the number of cycles, based on the number of points in a cycle. And then of course, once you integrate you get theta, you can get the theta v is actually vacant sites, you can calculate E, you can calculate k1, f k1 vacant sites, theta v gives us the current, and then you can go through the FFT. So, process is the same, it is just that you need to get the steady state values using numerical methods here. You have to do the integration with the correct expression for the k1 and k2. Otherwise, whatever we have done with Langmuir-Isotherm model for small or large amplitude perturbation, we have to use the same methodology here. So, that way numerical method is pretty much the same, there is no extra difficulty in applying it for a Frumkin or Temkin isotherm model or any other isotherm model compared to applying it for a Langmuir-Isotherm model. In case of analytical solutions, it is possible only for small amplitude perturbation. In some special cases you might get it for larger amplitude perturbation, but by and large it is possible only in the linear regime, and that is also relatively easy to do only for Langmuir-Isotherm model. Okay. Just as an example, so if I set the amplitude EAC 0 to 10 millivolts, I get spectrum as shown by this continuous line here. If I set it to 100 millivolt, it is little different, but in terms of the difficulty in getting these results, there is no real difference. Okay. For the given set of parameters, it is one adsorbed intermediate, it gives you two capacitive loops, one capacitive loop is coming from charge transfer resistance and double layer capacitance. The second capacitive loop comes from Faradaic process, and of course, if I give a two step reaction, for example, with 2 plus solution plus another electron. Okay. Depending on the parameter values, I can also get inductive loop. So, even here when I have n adsorbed intermediate, I can get n plus 1 loops. One loop is for the double layer capacitance in parallel with charge transfer resistance. Every intermediate, adsorbed intermediate would give me one time constant or one Maxwell pair. Okay. The rate constant could be described using Langmuir-Isotherm model or using Temkin isotherm model or Frumkin isotherm model. It can be complex, but we will not get more number of loops because of that. That is also something I would like you to note. So, in summary, using numerical method, it is quite straightforward. Okay. To simulate the impedance spectrum is to get the steady state values to simulate the impedance spectrum for reactions where the intermediates do not necessarily follow Langmuir adsorption isotherm. And although I have shown only the impedance results here, it is pretty straightforward to extract the second, third, nth harmonic from this. Okay. And whatever precautions we took in terms of waiting for certain time to get steady periodic results, we have to take the same precautions here also. Otherwise, what we get is in the unstable region.